Okay, so let me start with the thing. So again, this is like continuing from what where we had finished off till yesterday. So today I'm essentially going to do a whole neural network over here. So a convolutional neural network, exactly what it looks like. So we are going to rely on 2D convolution operations as of now, but let me start with this classical example. So say I have an input over here. This is X, and this X belongs to 1 cross 32 cross 32. Now I have over here 6 convolution kernels. This is P1, this is P2, like this. This is P3, P4, P5, P6. Okay, so essentially I have P, which is this concatenation of P1 up to P6, which belongs to R power of 6 cross 1 cross 5 cross 5. Okay. And then I have my biases. This is B1, B2, B3, B4, B5, B6. Now, as a result of this, I obtain an output tensor, which is Y. Now, can you please tell me what will be this dimensionality of Y? So this is a 2D convolution if you look at it very clearly. So this is a 2D conv operator. So now can you tell me what will my output look like?
Six cross 28 cross 20.
6 cross 6 cross what?
28
cross 28. Okay. Now let me do another thing. Within convolution, there is another factor which is called as stride. Now what this stride essentially means is, stride is called as step size. So it gets this name from the fact that when we are walking, so we have a certain step size in which we walk. So if we are taking long stride walks, which means that my footstep size is longer. If I'm taking short stride walks, then my footstep size is shorter. So that's the essential purpose of stride over here. Now, when I'm looking at stride, essentially, then let's look into what happens. So, say I had an input like this. So if I'm doing it with the so one of this example is with the stride equal to 1. Another is with an example of stride equal to 2. Okay. So when I'm operating with a stride of 1 and say a kernel, this P is equal to R power of 1 cross 2 cross 2. Then this is going to be a first location in either of these cases. So in case of stride 1, this is going to be my first location, which I fill it up. Next, when I operate with stride 1, my next location is going to be this. So I fill it up over here. The other location after that is going to be something like this. Now, if I'm walking with a stride of 2, I would see that the next location which I get is this. Then after that, I have my stride of another stride of 1, which comes over here. So I get this location. Then I come to this location. Now that is itself going to be the next element which I get down over here. So now essentially what it means is that stride controls the step size of the movement and nothing else over here. So that is going to essentially guide what is the steps in which I am essentially moving over here. Okay. So now if I have that, then let's look into it. Okay. So if I have an input X where this X belongs to R power of C cross M cross N. This is convolved with a kernel with that set of kernel P or PKs. So if I write down that this P belongs to R power of K cross C cross H cross W. And then you have your bias B, which belongs to K cross 1. Then my output is going to be Y, where this Y belongs to R power of K cross OH cross OW. Now, if I'm operating, so if the conf is with a stride of SH, SW, then I will get down OH is equal to what? So this is my question. So earlier when this stride was with a stride of 1, your output in the horizontal, the span of the horizontal direction or the number of columns which you have is
It should be m minus h divided by sh plus 1.
okay. So are you sure with it?
Yeah, I think m minus
M
h
minus H by
divided by sh plus 1.
this is what you are saying.
Yes, yes, sir.
And your OW is going to be N minus
W divided by SW plus 1.
okay. Now the question is, how did you come to this one? How did you derive this output form?
It should be like an AP series. Uh, I think it should be like an AP series. We are striding until the last form, and the progression is the S.
See, there is nothing so complicated to say. It's very simple. So what is the span of items over which you can span, which is M minus H? Okay. So
Yes,
I'm excluding the last point. So it is M minus H. Now this is the distance. Now my step size over there is SH. So the number of steps I am going to take is M minus H by SH. Earlier when my step size was 1, So I'm spanning over the complete length, every single integer spacing, but now I'm dividing it by the integer step size over there, which is my sh. So it becomes m minus h by sh. And because the last location is something which I need to take, so I will take that one over there. So this is how it comes from. However, what you need to consider over here is that if your m and this m minus h is not an integral multiple of sh, then you might get down a fractional number. So this is what creates a problem. So there is a, in most modern libraries for deep neural networks, there is a escape route over there. So it essentially considers a ignore condition. So what it would do it, the additional number of steps which it has to take, it will assume that all the other values over there is 0, and then it will continue with that one. Okay. So now if I have this kind of a condition,
Sir,
then yes, tell me.
but the recording hasn't been started yet.
The recording is going on. It says to me that the recording has started. Meeting
Yes,
is
I started it. So I started.
Yeah.
Hello, sir.
Yeah.
Sir, like you just said that the that m minus h by sh, that should be an integer, right, sir? Like, or else there will be a problem.
Yes, m minus h by sh should be an integer. Otherwise, if it's a fractional number, then can you have the size of a matrix as a fractional number?
Sir, why aren't we going for some assumption like floor or seal? Like, what will it lead to?
So essentially, it actually does a sealing operation over there. So essentially, if I write it down, then what a library is going to implement is a sealing function on top of it. This is what it implements.
Yes, sir. That is what I was telling. Okay, sir.
So kindly move to the next slide, sir. Slide is not.
I haven't yet done anything on the next slide. I just created a slide. Okay, so now say for this example which we were taking, where my x belong to r power of 1 cross 32 cross 32, and my p. Yes.
In the previous means in the floor, in the ceiling one, like if we are adding one, then shouldn't it be like flooring? Means either we could remove that one.
That one is to consider the end condition over there.
But sir, like with a like it is not certain that for a given stride we will have a full one at the end. Like let's say that there is the total length is 6.
You are right.
And we have a kernel of 3, and I give a stride of 2.
Yes.
So,
you are right. Actually, it does a flooring. Yeah. My thought was wrong because I was considering it as that additional, but it actually does a flooring plus that one. That's where it comes down to the right point. Yeah. Okay. So now say for the condition which we had in the earlier one, where then this P, the convolution was 6 cross 1 cross 5 cross 5. And you had B, which belonged to 6 cross 1, and this is being operated. So this is a 2D conf with sh comma sw is equal to 2. So in case this is how it was operating, in that case, what would be my y? So what will be the size of y in this case?
Six cross 14 cross 14.
So this is going to be 6 cross 14 cross 14. Why? So your OH is equal to m minus h by sh plus 1. So this thing M is 32 minus you have H which is 5 divided by SH which is 2 plus 1. So what does this become? 32 minus 5 is 29 divided by 2 plus 1. So
27 by 2.
27.
sorry, 27 by 2. 27 by 2 divided by 1. Now 27 by 2 is how much? 13 point something. So that is 13 plus 1, which makes it 14. Okay. Similarly, your OW will also be N minus W by S W of floor of it plus 1, which also ends up becoming 14. Okay. So now what you can see is that you can actually control the size in which you can get your output parameters over there. Now there is also another thing which is called as padding. Now what does this padding do? So the padding's role is, yes.
Sir, is there any reason behind ignoring the last column when n minus w is not the exact multiple of the stride? Because like if we add another column, means like if we are ignoring the last column completely, as we are taking the floor, then that means that we have ignored the last column, right?
No, we did not ignore the last column.
Because m minus h, the remaining m minus columns which were left, and as those were not the exact multiple of SW, then we have not gone till the last column. It is like that now, if we have taken
No,
the
no, wait. Let me go to the next slide, and before starting padding, let me clear it off. You need to visualize it and then you will get a clarity in this one. So say I had this this 3 by 3, okay, and I'm convolving it with a 2 by 2. And this is with a stride equal to 2. Okay. Will it work with a stride of 2? No, it will not work with a stride of 2. I have to take a bigger one. Wait.
As we are going with the stride of 2, so 3 minus 2 will be 1, and 1 is not the multiple of S. So we will ignore the last column, right?
No, wait. Let me take a bigger one, then it becomes easier. So this is my X, which belongs to, and then I have my P over here, which belongs to, and then I am convolving, and then I get my output. So my first location, and this is with the stride equal to 1. So my first location over here is over here. My second location with a stride of 2 is going to be over here. My third location is going to be over here. Now these two are being ignored. Now what I get over there is this one, then this one, and then.
Sir, we are taking stride of 2 if you are doing that.
Yeah, I'm taking a, I wrote down 1. So I moved with a stride of 2. Now let me get this OH. So that is M minus H by SH and a floor. So this becomes 5 minus 2 divided by 2 plus 1. So 5 minus 2 is 3 by 2. So 3 by 2 is 1.5. Oh, wait. If I take if I am taking a floor, then it's actually ignoring.
Yes, sir.
Yes, then you were correct. So if this is ignored, now this is something we'll have to actually check with the libraries because different libraries consider it in different way. Then this is ignored. And in order to, so the trick which we used to do classically. So I think in PyTorch version 1, they have a flag over there that you can ignore the ill fit conditions or you can auto pad it over there. But in general, my advice and how you would see most neural networks are defined is where they ensure that this inside part is always in fraction. So this is ensure that this one does not turn out to be much of a fraction.
So, sir,
Output is always in integers.
If we would have considered seal, then like if we have considered the condition of seal, then this last column would also have been considered, and then
Yes.
the
If you are considering seal, the last column will be considered. If you are considering floor, then the last column will not be considered. This is the point.
so do it depends on us that whether we consider seal or floor, or is it the rule? Means I'm not able to understand. We can take
So
it as per our convenience, or
it is as per your convenience. There is no rule. Okay. So what will happen is that if the last or boundary is to be ignored, then specify it to the function. I mean function call in your library, and then essentially your OH becomes M minus H by SH and fluorine plus 1. If this is to be considered, then don't ignore it. Then this OH becomes seal of M minus H by SH plus 1. Now, in your library call, there are certain default constructs. So it depends on which library is going to. So if you are using TensorFlow, it will have a default construct. If you are using PyTorch, it will have a default construct. But all of them will actually
but
allow
if you
you to
ignore
choose.
it, sir, but if you ignore it, we are going to lose some information on the edge, right?
In the boundary, you will lose out information.
But
Yes.
if we use seal function, then that means we are using padding itself. Otherwise, we not get the column value.
So that's where I'm coming to this point of padding. What we actually do with padding.
Hello, sir.
Yes.
Hello, sir. Sir, due to this ignoring this means that case, also the stride, if we take the means 2 or 3 means the stride amount, so we are going to lose the features also. Means
Yes, the stride
features
actually has an aspect of what we call as spatial subsampling. So stride essentially subsamples.
Yes, sir. Means is there any condition means what we take the means maximum stride amount?
These are all, so understand it. Deep learning has all of these as hyperparameters which are up to the designer's prerogative. Now condition of this is not dependent on one layer. The condition of whether I will take a stride or not, whether I will pad or not, it dependent on the structure of the network. We are looking at one layer as of now. So currently I'm focusing on explaining you what are the operations and how they operate. What parameter I would choose for an operation is going to be next when we actually open up a complete network and discuss with respect to a network. So the characteristic of a network is dependent on every single operation which is present in every single layer. Now, a layer's choice, what will be my parameters of a layer, the design parameters of a layer is not left only up to the layer. So there is nothing called as performance of a layer. There is something which is called as performance of the network, and that guides what is going to be the parameters which you choose in order to define a layer. Currently, what we are focusing on is defining the mathematical operations and input-output relationships of the layer, given that this is very critical for you to understand exactly what happens in the underlying library. Otherwise, without this part, you will not be able to get exactly what's happening in the underlying library. Okay, just hold on. We are going slow. I'm taking you slow one by one forward. You will not be able to write your first neural network until the next week itself.
Yeah, sir. When one problem is given, means when the network is built up, then it will take combined with the padding and the stride and all, right? When the
Let me come to padding. You have read it from some YouTube video somewhere here and there, and then you want to drop in all of those bunch of points in the class. That is not going to be of anybody's help. So if you want to go through this class, first and foremost, there is a request to you, whatever you have studied anywhere else. So my basic assumption is everybody knows everything of deep learning. Okay. And my basic purpose over here is by the end of this class, I will make you realize that whatever you have listened about deep learning and you have studied from somewhere else, you know it wrong. There are several misconceptions which you have as of now. So just take the flow and go forward. So the topics which I am covering in most other places, you would see this being discussed in first 5 minutes, and where there is no clarity on how exactly a certain thing works. Now I am trying to make it clear to you. So let's go with that flow. So let me come to padding. You have a question of padding, you can ask me after I finish off padding, because most likely the question around padding, question around stride, all of this will get resolved once I finish it off. Just hold on. When I tell you that we are finished till, so when we finish till a topic, then you start asking that question for the topic. Otherwise, the remaining of the class is going to get confused as to where did that topic come from suddenly. Okay, so for padding, here what happens is, say that I have this kind of a input being given over here. Okay. Now, if this is my x and say that this is my y, and if I am just convolving with stride equal to 1, then sorry, this is not y, this is p. In that case, my resultant y over here is going to be what? So in this case, it's also going to be a 2 by 2. Now, if I want, so is there a way to have y belong to r to the power of 1 cross 3 cross 3 when x belongs to r power of 1 cross 3 cross 3. So essentially what I'm saying is that is there some way I can still ensure that the size of my output is the same as the size of my input. Now in that case, what we can do is we make use of this whole concept of padding. So what a padding does is something like this. Now if I pad it, what I'm trying to do is something like this. And I have this internals over here, which is preserved. And on the outside, I am adding certain zero values. So these values over here, for my case, I call them as zero values, which I added. And this operation is typically called as zero padding. Now, zero padding is not the only type of padding. You can have reflective symmetric padding or anything as well. Now, what this would make is I get a modified version of X, which I called as X1, which now is 1 cross 5 cross 5. Okay. Now let us look into that convolution. In that case, this resultant over here is going to look like what? So I have a core region of 3 cross 3, which got expanded into this 5 cross 5. So my X belongs to, so my X belongs to, and this is my X1, which belongs to, and then I convolve this with this P, which belongs to, and this is 2D conv with stride equal to 1. Now, because the convolution is working on X1, so this output which I get over here is going to be Y, which belongs to R power of 1 cross 3 cross 3. So now you would see that the size of X and size of Y are the same. Here, same size of matrix which is obtained over here without any kind of a problem. So this is what you will be able to achieve by things like padding. Now comes the next question, that if I take padding into consideration, then what will be my size of my output? So what will be OH? So my OH is now going to look like M minus H plus 2pH divided by SH plus 1, and my OW is going to look like N minus W plus 2pW divided by SW plus 1.
Hello, sir. Hello, sir.
Yeah, tell me.
Sir, the dimensions of Y should be 1 cross 4 cross 4, right?
Should it be 1
Yes,
cross
sir.
4 cross 4?
Yes, sir.
Oh yes, it should be 1 cross 4 cross 4. So essentially I increased the size. Then this was a wrong example which I was taking. Yeah, if that kernel is not that, then it will be. So this is 1 cross 4 cross 4. So instead of writing this as same size, this should be that I have an increase in size. So let me take an example for which is from a practical network. Instead of giving you a smaller network, I will give you a practical network on which we do this kind of a thing. Okay. So a practical network is something like this. So I have an X which is of 1 cross 32 cross 32. I have a P which is of 6 cross 1 cross 5 cross 5. I have B which is of 6 cross 1. And I have 2D cons with SH comma SW equal to 2, PH comma PW is equal to 2. Okay, so if I have this kind of a situation, mm, 32, wait, no, my stride is 1. My stride equal to 1. Okay, if I have this kind of a situation, then what comes down? What will be my OH? OH is equal to M minus H plus 2PW by 2PH by SH plus 1. So this is going to be M is 32 minus 5 plus 2PH is 4 divided by 1 plus 1. So what is this going to be? So this
32.
is 27.
32.
So this is 31. 31 plus 1 is equal to 32. Okay. Similarly, my OW also becomes 32. So my Y is now going to be R power of 1 cross 32 cross 32. Now, essentially, I managed to bring my Y to the point of the same size as that of, say, my input. But definitely, I mean, although it's of the same size as that of my input, but that does not necessarily mean that I have my
Sir.
boundaries which are also completely covered.
So 6 cross 32, shouldn't it be 6 cross 32 cross 32?
This will be 6 cross 32. Yes.
And sir, like the dimension of P should be 6 cross 5 cross 5, right? Instead of 6 cross 1 cross 5 cross 1.
No, it will be 6 cross 1 cross 5 cross 5 because there are 6 convolution kernels, each of 1 cross 5 cross 5. So we are still considering the channel. I mean, it's a single channel tensor.
Okay, sir.
You look into your X. X is 1 cross 32 cross 32. So similarly over there, you have to have that one as well.
Is it always possible to find a pH and a PW such that the output size is equal to the input size?
You have to play around with it. Definitely you can.
Okay.
So I'll tell you something. Okay, wait. Let me tell you that interesting. So say there is a particular data set called as ImageNet. So in ImageNet, what you have is this images X. They belong to the dimension of 3 cross 227 cross 227. There are two variants. One is a 224 cross 224, another is a 227 cross 227. We are not going to look into that 227 cross 227. Now, if I have this X which belongs to 22 cross 7 cross 227, and if I have this P which belongs to R power of, say, again the same 6 cross 1 cross 5 cross 5. Okay, and I have my B which belongs to R power of 6 cross 1. And now I am operating with a SH comma SW of 2 comma 2 and PH comma PW of 2 comma 2. In that case, what will be my OH?
So one question.
Yeah.
The number of C channels in P is 1 or should it be 3?
So this will be 3. Correct. This has to be 3, otherwise it will. So you have 227 minus 5 plus 4 divided by 2 plus 1. Now this becomes 227 minus 1, which is 226 divided by 2 plus 1. 226 divided by 2 is 113. 113 plus 1, which becomes 114. Okay. Now you would see what essentially happened is that this OH is approximately m by 2. And it's just tad bit lesser than m by 2. M by 2 would have been 113.5. So the closest approximate integer is like this. So now what I have managed to do is I managed to both subsample, which is bring down the size of this particular output tensor, as well as have the convolution operation. Both of them go in one shot. So I could manage to reduce the size of the convolution tensor as well as also have the convolution operation being going down over there. Okay. Now from here we'll get into the next kind of an operation which is called as pooling. So the pooling operation is something like this. Yes.
Sir, if you told about zero padding, we are putting zeros over the matrix. But zero means, sir, we are putting a black boundary over our image.
Yes.
Sir, so isn't it better if we use some average value or something, like if we have a picture of garden, so we should put something which is similar to in the boundary?
That is, yes. So that is called as reflective symmetric padding. So what you do is you basically clone as a reflection from that last column.
Yes, sir, because I was.
So you can do reflective symmetric padding. The only thing is your performance and everything will be better than the zero padding. The only issue is that a reflective symmetric padding is actually a very costly operation. Here what you do, you have a bigger sized tensor which is full of zeros. In the center you just go and fit this one and done. In case you want to do a reflective symmetric padding, you'll have to reflect the image. So there will be if else conditions and everything which you will have to put and do it. And then you will be able to create it.
But we have to go for numbers. We have less number of iterations, sir, in that case, if we are getting better image sooner.
No? See, honestly, that is something which you are speculating, but nothing of that sort will happen. The reason why it will not happen is that barely your objects of interest are at the periphery. Objects of interest are generally in the middle, and those with loss of periphery, you don't lose a lot. What you need to, as a designer, now this is something which is of importance. So if your padding is of a very high value, then you would see that if you are padding with a very high value, then you would keep on rapidly losing out from the periphery. Now I don't want to do that. So as a designer, you will now have to be very cautious with what is the width with which you are going to pad everything.
Okay.
Okay, so now comes this whole aspect of pooling. So what pooling does is something like this. Say I consider this particular block which has a certain width and a height. So I have a pooling span Now a pooling span is basically defined as what region I'm going to pool it. So it has a width of W and a height of H. Say, then what this pooling is going to do is there can be multiple operations. One can be max pooling. There can also be another thing which is called as average pooling. There can be another thing which we can call as minimum pooling, min pooling. So essentially what it does is it operates on the samples within this span. So if we take this example over here, let's say I have this 3 by 3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and I am doing a 2 cross 2 pooling. Then I take this particular location first and I'm doing what? 2 cross 2 max pooling. So what will be my resultant? What is the maximum value within this span?
5, sir.
5. This is 5. Okay. Now I would move to the next location, which is over here. So what is the maximum value over here?
6.
That is 6. Now I will come to this location. What is the maximum value?
8.
8. Then I have this remaining part.
9,
When
sir.
I'm going to pull, this is going to be 9. So I get a resultant which is a 2 cross 2 and this is what it comes out. Okay. Now if I run a 2 cross 2 average pooling, then what will it look like? So my first location is going to be average of 1, 2, 4 and 5. So how much is that? 6, 7, 8, 9, 10, 11, 12. 12 divided by 4, which is going to be 3. Next, for this one is going to be 8, 9, 10, 16. 16 divided by 4 is going to be 4. Next over here is going to be 12 and 8 is 20. 20 and 4 is 24 divided by 4. So that is going to be 6. And then I have 9 plus 5, which is 15. 14. 14 plus 6 is 20. 20 plus 8 is 28. And that divided by 4 is 7. So if I'm doing an average pooling, then I'm getting this particular kind of a value which comes out over here. Okay. Now, as a result of this pooling, whatever is this y, whatever you get, so this will have a certain size of C cross OH cross OW when your X belongs to C cross M cross N. Now here you can actually again write it in the same way. So your OH is essentially going to be M minus H by SH plus 1, and your OW is going to be N minus W by SW plus 1. So these are your values of OH and OW which you get from here. Now something you need to keep in mind is that if I have a multi-channel tensor, then this operation is something which is carried out on a per channel basis. So what I meant to say is that say I have a two channel tensor Y, which belongs to R cross 2 cross 3 cross 3. Okay, and then say that these are the values what I'm writing down over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is my Y of 1, and this is my second one, which is Y of 2, comma, colon, comma, colon. And say that the values in this one are something like this. Now, if I'm doing a max pooling over here, then I get down these values. So what are these values? This is going to be, the first one is 5, 6, 8, 9. This one is going to be 105, 106, 108, 109. So this is, why did I write it as Y? This is going to be X, because that is an input. So my input is always going to be X. So this one becomes my Y of 1, comma, colon, comma, colon. And this becomes Y of 2, comma, colon, comma, colon, which is over all the elements over there. Okay. So one thing to keep in mind is number of channels in input is same as number of channels in output. Okay. So now from here, if I take that example with ImageNet, so your X belong to power of 3 cross 227 cross 227. Okay, and you had your P, which belong to our power of 6 cross 3 cross 5 cross 5. You had your B, which belong to our power of 6 cross 1. And now you are operating with the SH, SW of, instead of 2 cross 2, now I'm operating with a 1 cross 1. But I have same PH, PW of 2, 2 given over here. In that case, what is my Y going to belong to? What is this Y going to come out as a result of 2D convolution? Tell me. What is going to be the size of Y as a result of this 2D convolution?
Sir, we are using max pooling, no?
I am not yet using max pooling. Why are you guys confused? I am just asking you a very simple thing. Just do a 2D convolution with this operation. Then tell me what is going to be
6
Y.
cross 3 cross 114 cross 114.
6 cross 3.
Yes, sir, because the number of P's are 6, right?
Actually, 6 cross 1.
Okay, 6 cross 1.
Why will there be 1?
6 cross 114.
114.
Ah. Will it be 6 cross 114?
So 229 cross 229. 6 cross
What
229.
is going to be OH equal to? OH will
114.
114.
So OH is going to be M minus H plus 2PH divided by SH plus 1.
So 227, no? It should be
227. So this is 227 minus H minus 5 plus 4 divided by 1 plus 1. What is that? 227 minus 1 is...
it should be 227 cross 227 itself.
So this is going to be 227 minus 1 is 226. 226 plus 1, which is equal to 227. Yes or no?
Yes.
Okay. So say that I don't want this to be 227, but I want this output over here to be something like 226. How can I achieve that? I mean, that's going to be complicated to achieve. I will not focus on that one. So now,
Sir,
if this is...
Sir, we could increase the size of the kernel if we want to do that.
So like 6 cross 3 cross 6 cross 6.
Yes, so it has to be an even sized kernel. Okay, now let me not get too much worried about it. Okay, so now here comes the problem. Here comes it. So now if I have a 2D convolution followed by a pooling operation. So what I'm going to try is something like this, that I have my input, which is X. It undergoes a a 2D conv, and then on this output over here I get a Z. Then this undergoes a max pooling, and then out comes over here a Y. Okay. Now if this 2D convolution is formally defined as, say, 6C. So what did I have over there? There were 6 convolution kernels, each of 5 cross 5. 6C, 5W, and what was the stride? The stride was 1 and the padding was 2. 1S, 2P. So if this is what I write down over there, then what this signifies? So we need to understand these are some formal naming conventions. So this part means that there are 6 convolution kernels. 5W means these are 5 cross 5 sized kernels. 1S means that stride is equal to 1. 2P means padding is equal to 2. Okay. Now, when I have this max pooling operation, so here also I need to define that operator over there. So in this max pooling operation, I define it as something like say 3W 2P. So what I meant to say is that this is with a span of 3 cross 3, and this is, sorry, not P, but this is tri. If we don't actually pad anything in case of a convolution, in case of a max pooling, and this is with the stride equal to 2. Now, if I'm looking at this Z, then what is this Z? Let's look into that one. So Z is R power of, what was that value? So as a result of this convolution, what did we get?
6 cross
227
6C.
So 6 cross 227 cross 227. This was Z. Now, what will be my Y? So definitely the number of channels is going to still be the same because it's going to apply on every channel. Okay. Now, if I have a span of 3 cross 3 and a stride of 2, then what will happen? So over here, it's going to be OH is equal to what? M minus H by SH plus 1. So M is 227 minus 3 divided by 2 plus 1. So 227 minus 3 is 224. 224 divided by 2 is 112 plus
So it
1.
should be 113. 6 cross
113.
113 plus 113.
Okay. Now look over here. So the size of this tensor is approximate, the resultant of this whole operation and the size of this tensor is approximately equal to the size of this particular tensor. Here it was coming as 114. So if we adjusted it, we could also have gotten 113 as such. But the size of these two tensors are almost of the same size. Okay. But there is a question that if you can have two different operations which produces almost the same kind of a same sized of output, then when do you use max pooling versus when to use strided convolution? So when do you use max pooling versus when do you use strided convolution? So do you have any thoughts on this one?
So when we need to have the channels separated, then we should use max pooling.
No, in either of the cases, you will have channels separated.
So when the input size is too high, like the number of pixels or the number of size of the matrix is too high, we can use max pooling so that the computational time reduces and it is not computationally very costly.
But look at the other side. If you are doing convolution with a lower stride, so essentially when you are using max pooling, then your stride in convolution is 1. So when I'm doing a convolution with a stride of 1, then the number of mathematical operations which I will have to do is much larger.
Yes, sir, but there are no parameters in max pooling. Like
There are no parameters is max pooling. So my point is something like this. So I did more number of mathematical operations in the convolution. So I consumed more amount of compute. Then again for max pooling, I'm consuming more compute in order to gain the size of output, which is the same as what I could have obtained anyways by doing a strided convolution.
But sir, in stride we are losing information. In max pooling, we are taking the best of that best information from that in matrix.
Yeah, essentially what happens is that sharded convolution is an average filter like operation, but it does not give you access to the highest activation, the highest value over there. That is something which you get in case of a max pooling. Okay. Now this derives itself from the basic concept. So all of these pooling operations belong to the general class of mathematical operations known as mathematical
Sir, are you writing
morphology.
something?
Huh?
Are you writing something on the Jamboard, sir?
I am writing something on the Jamboard and the Jamboard is shared.
Okay. Okay.
Isn't it updating?
Yes, sir. It's updating.
It is.
Okay, sir. I guess.
Or order statistics. Now, in simple term, if you want to look at it, there's a very simple example which I generally give. So say that there was there is some sort of a spike in your activation over here, which is 20, and it is 1, 2, 3, 4, 5, 3, 2, 1, something of that sort. So if I do a max pooling 2 by 2 and stride 2 by 2 over here, then what will you get down? It's supposed to be a 2 by 2 matrix. So where you will have this 20, 20, 20, 20. Whereas if this was run through a convolution, which is approximately average filter, and that can be approximated as an average pooling, you'd still get a 2 by 2. But the difference is that this 2 by 2 is going to have the average value. So this becomes like 22.
So in the above
plus
case,
6.
we are using stride of 1 cross 1, right?
So stride should be 1 cross 1, right?
Stride of 1 cross 1, sorry. Now here, this one is going to be 20 plus 2 is 22 plus 6 is 28 divided by 4 is 7. This one is going to be 20 plus 6, 26 plus 3 is 29. 29 divided by 4 is approximately 7. Then this is 20 plus 6, 26 plus 2. This is also going to be 7. And this is going to be also 7. Okay. Now, if you compare between these two, in this case, this high activation is preserved. Here, this is lost. So typically, like down the line of a neural network, so I will actually, when we visualize the activations of a neural network, you will write down a code and you will yourself see. You would see that if a certain object is activation becomes high at that particular location, and we are somehow supposed to preserve how that thing keeps on going over there. So that can be preserved if you are doing these kind of max pooling like operations. On the contrary, if you are doing a standard convolution with stride or doing an average pooling like operation, then you tend to blur it out. And these high activations are not preserved. So that is something which we don't desire to have at all. So that's one of the reasons why we go on with having these kind of operations which are called as max pooling. So are we clear till here?
Yes, sir.
Okay. So now I'll take a quick 5 minutes break before we start with the next one, which is about a transfer function. Okay, guys, I'm back. Let us resume once again. Now, the next part over here after pooling is what we call as a transfer function.
Sir, I have a doubt. Like,
Yeah.
will it be right to conclude that we should never use a max pooling if we have an image data set with lighter background? Because it will just extract the back, it will just absorb the values of background and then lose all the information about the main image itself.
No, you cannot say that, because what you have is you have a lighter background, but then
Yes.
the activation is not just a function of the background. It is function of background and the convolution with that convolution kernel. Okay. Now say you had a lighter background and your convolution kernel had everything which was a negative value. So what it did effectively was it inverted the image. So all the bright regions have now become darker. All very high positive values have now become very high negative values. Okay, so now if I run that one through max pooling, then the bright region will not come.
Right. So max pooling should always be done after convolution, not directly on the image itself, not on the data.
So nobody really restricts you. Honestly, for these layers over here, it has an input, it has an output, and this is the relationship how you define it. Now, what will be your subsequent ordering in which you will place your inputs and output is going to is a designer's prerogative. Okay, so we will come to that. Like, why does certain thing precede another thing? From a mathematical transfer function kind of a point of view, not transfer function. So, say from a mathematical function understanding, it really does not have any implication. My size of tensors will still be the same. What is the nature of response which I desire is going to guide how I am going to place these blocks one after the other.
Okay, sir.
Any more doubts?
So why do we need many filters? Like every filter does the same job, right?
No, every filter is a unique filter. See, what did we have? Every of those weights are separately tuned. So if every filter is separately tuned, it's a different entity. They are not coupled. I did not say that W1 equal to W2 equal to W3. Each of them is different, or P1 equal to P2 equal to P3. Each is different. So they are going to learn different attributes. Although we haven't yet come to the learning part, we are still doing the forward pass and understanding what happens in the forward pass of it. How to tune and modify those weights is something we are still to again get back to.
Sir, hello, sir.
Yeah.
Sir, why do we say that like higher activation values have more information? So like we are aiming to preserve the high activation values, right?
Yes, we aim to preserve the high activation values. This comes down from the whole theory of autocorrelation. Okay. So do you know about correlation, right?
Yes.
Okay. So say there are two functions whom I am correlating, or there are two signals or whatsoever I am correlating them. Okay. Now, when will I get the highest value of correlation between them?
So when they are like exactly same or
When they are exactly overlapping one another, there is
yes.
complete alignment, total alignment. Okay. Now here also it's the same kind of a stuff which will happen in a CNN. So because I have reflected it on horizontal and vertical axis, so my resultant convolution operation can now be written down as a autocorrelation operation, as a correlation operation. Now correlation operation is going to give you the highest value at the location where the object in the image matches with the shape which is present in the convolution kernel, or that whatever is that P kernel over there. Okay. So say that there is an apple and there is a kernel which looks like an apple. Now you will get the highest activation at the place where exactly the apple is located in the image. On all other places you will get down low values. Now if I wanted to make a classifier whose job was, if there is an apple, then say that there is an apple. Now, what I would want to do down the line when I'm building this classifier, I would like to preserve this high activation whenever it found an apple.
Yes, sir. Yes, sir.
That's the
Yes,
reason
got it.
of having max pooling.
Yes, sir. Okay.
So one more thing with regarding stride.
Sir,
Sir,
is it not possible to preserve the activation? Hello, sir.
Hold on. I think Hitesh was
Sir, you
asking.
told.
Let
Okay.
Hitesh finish, then we.
Okay. Okay.
So my point was that if we are taking stride, which is less than the size of the kernel, then we will be taking similar areas again. Overlapping will be there. So won't be it a waste of resource? Like shouldn't we take like a stride like always equal to the size of the kernel?
The general practice is to take stride equal to size of the kernel. But as I said, this actually comes from the broader field of order statistics and mathematical morphology. So if you recall in image processing, you study about something which is called as erosion operation, dilation operation, these kind of stuff. So if you look closely over here, a max pooling is essentially equal to a dilation operation. In dilation operation, what were you doing? You are taking max of all the values in case of grayscale dilation. In binary, this max of all the values becomes union of all the values. So that's the point. So it depends on what we are aspiring to achieve.
But
that's what I said. So deep learning heavily is biased towards the designer's intuition and the designer's expertise. And we haven't yet got into a complete neural network design. We are still learning about the building blocks and bricks of a neural network.
Okay, sir.
Okay, Vinod, you may continue asking your question.
Yeah. Sir, yeah. So you are telling that this max pooling is mainly to preserve the high activation. So my doubt is it not possible to achieve similar result by carefully choosing the kernels? If you choose the kernel values, even then we can preserve the the high activation values, right?
So what you are saying, I do get your point. So you are doing a strided convolution.
Same strided convolution, but different kernels, so that I will achieve the same result what I am getting with the max pooling.
So now let me tell you this thing. So say you had an apple somewhere in the image, and your convolution kernel also looks like that apple. Okay, but because you had strided way, you are doing a strided convolution. So your convolution kernel does not exactly overlap on the apple. So either it is overlapping on the left half of the apple. The next stride is when it is overlapping on the right half of the apple. So in that case, will you ever be getting down full highest activation?
Yeah. Okay, sir. I understood. Understood. Yeah. Correct.
So that is the reason why I would still do a stride equal to one convolution so that I can find an exact match. But I still want to reduce the size of those activation and preserve the location of that exact match. So now I will do a max pooling operation.
Excuse me, sir.
Yes.
Sir, I have a doubt from yesterday's class. So yesterday you created a diagram in which you said that basically you created that number of filters is less than number of channels of images. Is it actually possible to do that, sir? Practically.
Wait, that was something related to the 3D side of it.
Yes, yes, exactly. But yeah.
That was to give you an analogy, but later on in the last part of the slide, I did write down about a multi-channel 3D convolution operation. So please follow that multi-channel 3D convolution operation. In fact, the number of channels and the depth of a convolution operation, they don't have any relationship between them. So in some cases, you can have depth. So it's something like this, that if I'm taking a multi-sequence MRI, I can have 7 sequences, which means the number of channels is 7, but I can take a depth of 3, which is 3 slices. This is possible. Alternatively, in case of video, where my number of channels is 3 because of RGB, I can have 100 frames. So that's like the opposite scenario where your number of channels is lesser, much lesser than the depth of that particular 3D tensor which you are taking.
Yes, sir, exactly. So my doubt is, so for example, if we can do that, so isn't that the bad idea since we are using the same filters to use learn various things? Because every filter learns a specific thing, right? So isn't
So
that a bad idea?
essentially, see, the number of convolution kernels you choose, or K, the number of unique filters which you are choosing, is one, it's a designer's prerogative. There are ways of how to change that. So I will in fact teach you about what we call as neural architecture search. So over there, what this essentially does is that if you have two lesser number of filter kernels, you might not be able to actually capture how many unique objects are present over there. And on the contrary, if you have more number of filter kernels, then you are increasing more number of operations, whereas multiple of them may be duplicates of each other.
Yes, sir, yes, sir. Got that.
Okay, so now let me come to the any doubts from like what we covered till now, or can I move to transfer function? Okay, then let's move to transfer function. So now here, what this does is, so say that I have this x which belongs to some particular way. So how I wrote it down as C cross M cross N over here. Okay. Now this, what is known to it is that x is real valued. So x can exist from minus infinity to plus infinity. Now essentially this is a unbounded scenario. And then is something which we don't prefer, because you don't have a control over how many bits you want to use for storing all of these information over here. Now if I want to get this into a bounded scenario, then what I can do is I can write down something like this. Y is equal to FNL of X, where this FNL is a non-linear transfer function. Also, sometimes they are known as activation function. Okay. Now, there are different ways in which you can write down these nonlinear transfer functions or activation functions. So one of them is given like this. So f nl of x is equal to sigma of x, also known as the sigmoid function, and this is written as 1 by 1 plus e power of minus x. Okay, so now look into this one. If x tends to minus infinity, then what will y tend to?
0.
Y will tend to 0. Okay, how? So x tends to minus infinity, so e power of, so as x is tending to minus infinity, this e power of minus x becomes e power of infinity. Now 1 plus e power of infinity is still e power of infinity, and any number raised to infinity is again a value which is higher than infinity. So this whole thing tend towards 0, 1 divided by a very high number. Now on the other side, if x tends to plus infinity, what will y tend to?
1, sir.
Y will tend to 1. Okay, so how will that happen? So x tends to plus infinity, which means this e power of minus infinity. So any positive number to the value of minus infinity is what tends to 0. So this becomes 1 by 1 plus 0, which essentially makes it 1, and that's why you have this one tending to 1. So now look into something interesting over here. So what this essentially means is that if I write down this input-output relationship over here, then so this is my x and this is my y. This is limited to 1. This is towards infinity. This is towards minus infinity. Then I have a system where this value comes like this and starts becoming like this. This is 0.5. In fact, you would put down that if your x is 0, so it becomes e power of minus 0 is e power of 0, which is equal to 1. So 1 divided by 1 plus 1, which is half, which is equal to 0.5. So this is what you will get down. Now definitely you see over here that your output is bounded in y belongs to open bracket 0, 1 when x belongs to open bracket minus infinity to plus infinity. So when even if your input is unbounded, your output is still bounded. Okay. Now this is one of the ways of doing it. Now there are other options of doing it as well. So one of them is what is called as, so this is the sigmoid function. There is another one which is called as rectified linear unit or RELU. So rectified linear unit is defined something like this, that FNL of x is equal to x if x is greater than equal to 0 is equal to 0 otherwise. So if you draw this response, then this looks something like this. That for all values of x from minus infinity till 0, the value is exactly 0. After this, it is the same, which is present over here. Now, this what it would do is that if x belongs to minus infinity to plus infinity, you will have y belongs to absolute 0 to open bracket infinity. Okay. Now these are again designers prerogatives on what you choose, but one of the factors over there is that because you will have a back propagation involved, so if you are doing a complete neural network, so you will have these layers as well, and when you have a back propagation involved, you will also have to take a derivative or derivative over this nonlinear function as well. So generally in a designer's prerogative part, one of the choices, like you try to take such kind of transfer functions where your derivative, computing the derivative is much more easier. So we'll actually get much deeper into this one where I will open it up and show you why. Because if you look into it, for a sigmoid function, the derivative is much more, you will have an e power of x derivative to be computed. Whereas for ReLU, the fun is that for any x, so for x less than equal to less than 0, you will always have this gradient which is equal to 0, and for x greater than 0, your gradient is equal to 1 always. So this is the fun part over here. So it's much more easier to compute the gradient of ReLU, although you can always come back and argue that you don't have a bounded output, a totally bounded output in the strict sense. You have a lower bound, but you don't have an upper bound over there. So once I get into an actual network, I will be able to demonstrate this much better.
Sir?
Yeah.
Sir, what does negative value represents in case in like physically information, like what does it mean by negative value?
Is a negative signal, that's it. So say I took a positive value image. An image is something which will always have greater than 0 values over there. And you had a convolution kernel where all the weights were negative. So I did that convolution. The resultant of that convolution is negative. If you come and ask me what is the physical significance, I mean, it's just the resultant of a system. That's it. There is no major physical significance associated with it.
So it's just garbage. What we have to.
Not garbage. It is a resultant of a system. You cannot call it garbage. You can call something with respect to when you have the complete system defined. So once we actually open up a complete network, we haven't yet defined a network. This is what I'm saying.
Yes.
You cannot comment on the usefulness parameters of a layer until and unless you have the complete network which is defined.
Okay, so like, why are we suppressing the negative values here in case of ReLU?
Why are we suppressing negative values in case of a ReLU? So ReLU is not used in all cases. There are very specific cases when ReLU is used. So I will come to that image based example when I will explain you why are we doing it for ReLU.
Okay, sir.
As I said, it's a designer's prerogative subject to the constraints given which you are solving. So till now, on a designer's prerogative, what constraints did you solve? You have just solved out only one constraint, which was like how many number of neurons in the input and how many number of neurons in the output. That's the only thing which you know and which you have solved. Beyond that, you haven't. We haven't yet designed a complete network. So we'll start with designing that network in the next week. Okay, guys, if we don't have any further doubts, then I would like to close for the day and then we catch up again next week on Wednesday.
Thank you, sir.
Okay, see you then.
Thank
Bye.
you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir.